It's a pleasure that I would like to introduce Alessio Sammartano from the Politecnico of Milan, that will speak actually from Italy at 11 o'clock at night on Lovász-Saks-Schrijver ideals. Thank you so much, Alessio.
Thank you. Thank you for the invitation. It's really a pleasure for me to be here. And I'm going to talk about this joint work with Laura Casabella, who's a PhD candidate at MPI in Leipzig. So let me start and fix the notation, introduce the main definition and characters. So I will be work over a field, algebraically closed and characteristic not true, and a vector space of dimension d with a symmetric bilinear non-degenerate form. And without loss of generality, one can just fix an orthonormal basis. And this is the same as working with k to the d, where the bilinear form is simply the standard dot product. Okay, so the sum of the product of the coordinates for each position. So this D is one of the pieces of data. The other piece of data is a graph. So G is a simple graph on n vertices. So I highlighted this D and N that they play a crucial role throughout this talk. They're the parameters essentially of everything that we're going to study. Okay, so in fact, we will study D by N matrices. Okay, so we are working in the affine space of D by N matrices, and I denote by S the polynomial ring of this matrix. Okay, so I have a generic matrix in as many variables as I need, and that's the coordinate ring of the space of matrices. Final piece of notation, and I will consider these polynomials, these quadratic polynomials Fij, which are the orthogonality relations. Okay, so let me call them orthogonality relations. They're the dot product of column I and column J of this generic D by N matrix, just encoding the orthogonality conditions between two columns in a matrix, in a D by N matrix. Okay, so then I can give the main definition of this talk, or at least of this first part of the talk. So this takes this name of three mathematicians working in combinatorics mostly, Lovász-Saks-Schrijver, and we can essentially define an ideal and then the coordinate ring, the variety, the scheme, and so on. So let me just define the ideal and the ring. I will denote it by L of G and D. So this keeps track of the graph, and D, the dimension of the vector space. So this is simply the ideal generated by these quadratic relations, this quadrix Fij encoding the orthogonality of column xi and column xj for all edges of the graph ij. Okay, so this has the notation LGD, and then sometimes it's convenient to talk about the ring, so I'll also introduce a notation for the ring. Simply RGD is the quotient of the polynomial ring by this ideal. So then it follows immediately that if we think about the variety defined by this ideal, so as a set, so the algebraic set, the subset of D by N matrices, these are precisely the matrices where column I and column J are orthogonal if Ij is an edge of the graph. And these such matrices are also called orthogonal representations of the graph. We can think of them as functions of the vertices of the graph, where from the vertices to our vector space, such that this subject to the condition that two adjacent vertices must be mapped to orthogonal vectors. So these are called, so this is the variety of orthogonal representations of G in K to the D. All right, so these are the objects we're interested in, and maybe this is a lot of notation, so let me make an example so that we go slow and absorb the notation in a simple case. If there's any question at any time, just yeah, feel free to interrupt me. There's no issue at all. All right, so in this small example, I've chosen D to be 3. So we're talking about vector space K to the 3, vectors with column vectors with 3 entries. And N is 4. So there's 4 vertices. And here's a graph on these 4 vertices. So the ideal as 4 generators, these are 4 quadrics generating the ideal corresponding to each of the 4 edges of this graph. So for instance, F23 is corresponding to the edge 2, 3, and it is the dot product of columns 2 and 3 in the generic matrix. So here's an example of a point in this variety of matrices defined by this ideal. So I can think of this as a quadruple of vectors in K3 that satisfy the orthogonality conditions dictated by this graph. Okay, so column 2, which corresponds to vertex 2, it has to be orthogonal to everybody else because 2 is adjacent to all the other vertices. And then the only remaining orthogonality conditions that I need is the one between 3 and 4, and this is verified. So this is large class of ideals. It's an interesting class of ideals for many reasons. I'm not going to spend too much time discussing the appearances of LSS ideals, but okay, this is a sentence you will always hear whenever there's a talk about ideals and graph. There is a rich interplay between the combinatorics of the graph and the algebra and the geometry of these ideals. But it's true. It's not just an empty sentence. It is really a very interesting interplay. And in fact, this story started in the combinatorial side with this work of Lovász, for instance, and this paper of Lovász-Saks-Schrijver from which these ideals take their name. And many subsequent works where basically there is a lot of the structure of the graph is reflected in the algebraic and geometric properties of these ideals and varieties. More recently, there were also some interesting connections to applications really to determinantal ideals. So to sparse determinantal ideals, where you, instead of having a full generic matrix or a full symmetric generic matrix and so on, you may have some zeros here and there. So usually the zeros are encoded by a graph, and then there is a precise connection between sparse determinantal ideals and this Lovász-Saks-Schrijver ideals of the graph. And I'm only going to mention these two, there's more. But actually, these ideals are also interesting for another natural reason. That is, we can think of them as a generalization, as a really big generalization of many familiar ideals in combinatorial commutative algebra. So for example, if D is 1, if we start in the simplest case, maybe when D is 1. So when D is 1, we have a 1 by n matrix. So really we have a row of variables. And the LSS ideals of a graph with d equal to 1 are precisely the monomial case. This is the monomial case, and these are the usual edge ideals, the monomial edge ideals, where you have a generator, a square-free monomial of degree 2 corresponding precisely to the edges of the graph. And as I'm sure you all know, there's a huge literature on this edge ideals. It's a trivial observation that these are always radical, but the fact that they're monomial, in some sense, they're too simple, and they don't really have a chance to have interesting properties of the in the sense that we're going to be interested later, such as being a complete intersection or being a prime ideal. This essentially never occurs for monomial edge ideals. But the study of the combinatorics of the components of these objects is definitely a huge research area. If we go to the next value, d equal to 2, this is also more recently well-studied class of ideals in combinatorial commutative algebra. It's essentially the class of permanential edge ideals. It's not literally the same, but it's essentially the same up to a change of coordinates. So when these two, what we do is we double our variables. We no longer have one row of variables, but we have a 2 by n matrix. So we have 2 rows. And then we also double our quadric. Okay, so the ideal now is as the same number of generators as before, so corresponding to, again, the edges of a graph. But now we have our previous term, and now there's a clone of the same term, but on a different set of variables. And these are not literally the permanence of this matrix, but as I explained, as I said, there's you can apply simple change of coordinates and rewrite this as an ideal of permanence. And this is still a radical ideal, although that now it's a non-trivial fact. So this is a theorem of Herzog, Macchia, Saedi, and Welker, who are also the people responsible for the name LSS ideals. And they're still relatively simple in the sense that they're binomial. They're not gonna have very nice properties in the sense of, for instance, defining a prime ideal, but they're nicer. And at the same time, what we see already in the jump from 1 to 2 is a considerable jump in complexity. A result that can be interpreted in this sense is a very recent result of these 4 authors, Gismondo, Wang, Schenk, and Weyman, who compute the free resolution in the case of the complete graph. Again, their point of view is that of the permanence of a generic matrix, but again, in the case d equal to 2, this is a highly non-trivial result. So it takes a lot of work to find the resolution. Whereas, for instance, for the complete graph, the resolution of the monomial edge ideal is essentially very simple. So these are the first 2 cases, and we see in these 2 cases we recover well-studied classes of combinatorial ideals, but the idea of LSS ideals is to not study d equal to 1 or d equal to 2 or a particular value of d, but to study the whole family for all d. And in particular, if we allow d to increase and d becomes sufficiently large, then the picture changes completely. If we think about these generators of the ideal, so these quadrics now, where we have d terms in the quadric always involving different variables, that means that that the quadrix has higher and higher rank as we increase the D. And this is not just a property of the single quadric, but really of the vector space of all they generate. So if we consider all this space of quadrics simultaneously, there's a notion of strength, collective strength due to an onion and oxter. For quadrics, it's essentially the same as the notion of rank. And this space has this nice property that you don't find any quadric of small rank in this set. So as we increase the D, we get an ideal that has a higher and higher collective strength. And then we can use this general theorem of an onion and oxter from 2020 that has nothing to do with LSS ideals. It's a general theorem, but if we apply it to our case, this says the following. So if we can think of fixing the graph G, or just fixing the number of vertices of this graph, or the columns of our generic matrix, and let D increase. So we essentially represent this graph in a bigger and bigger vector space. Then the ideal, or the coordinate ring, will have nicer and nicer properties. So at some point it will become a complete intersection, and then it will become also reduced, and then the singularities will get better and better, and then it will be a domain, and then for higher D it will be normal, UFD, and so on. So as I explained, this is a general theorem of an onion and oxter, the one that was used to prove the Stillman conjecture. And but it's a theorem that is so general that it cannot provide effective bound in practice. But in our context, it's a natural. Then it's an interesting problem to seek effective bounds for these properties. And these are not just some random properties, these are also the natural properties that we look, for instance, when we do some applications to determinantal ideals, as I explained earlier. Okay, so this is going to be essentially the theme for much of what follows. When can we expect analysis ideal to define a complete intersection or a normal domain, and so on? The first main class of results is in the following paper of Konka and Welker, who proved, among other things, the following two important properties of LSS ideals. So first of all, about the properties of being prime and complete intersection. They show that they're very closely related, so they're almost equivalent in some sense. To be more precise, prime implies complete intersection. So if the LSS ideal of a graph in some dimension D is prime, then it's also a complete intersection. And the converse is not necessarily true, but complete intersection implies prime for the next dimension, for the next value of D. And then obviously you can continue this chain, and this will imply complete intersection for LG D+1, and then prime for the next, and so on. So in other words, this item 1 is telling us that not only these properties are satisfied for sufficiently large D, but in fact, there's a threshold such that below the threshold, the ideal is not prime, and above the threshold, the ideal is prime for all integers, and another threshold for complete intersection. And then these two thresholds are either the same or they differ at most by 1. the second result has to do to actually finding effective bounds for effective concrete sufficient conditions for all of these to happen. And unsurprisingly, this has to do, as I was saying, has to do with the combinatorics and the structure of the graph. So Conca and Belker introduce a quantity associated to the structure of the graph called positive matching decomposition number. I don't really want to define it here, but there's a threshold that there's an invariant that depends on the structure of the graph, such that if this is above this number, then the LSS ideal is radical and a complete intersection. And then by the first part, if d is above this number plus 1, then it's also a prime ideal. Clearly, this bound will change from graph to graph, and if we want to have a simple a uniform bound, a theorem only in terms of n and d, then the results of Conca and Belker amount to the following corollary. When d is at least 2n minus 3, the LSS ideal will be radical and complete intersection. And when d is at least 2n minus 2, the next value, then we know for sure that the LSS ideal will be prime. Another natural property to consider is just when are these ideals radical? Are these ideals radical just without worrying about complete intersection? We've seen they're always radical in the case of edge ideals and in the case of permanent edge ideals. So these are the cases when d is 1 and 2. But then this is not necessarily true as you keep increasing d. So again, Conca and Belker find an example of an ideal of a graph in K3 that is not radical. So we know that the property of being radical will stabilize at some point, but below that point, it might behave somewhat erratically. But then Conca and Belker formulate a conjecture about radicality that basically they expect this to hold for the complete graph. So Kn denotes the complete graph on n vertices, and then they conjecture that for all n and for all d, the LSS ideal will be radical. Let me anticipate that the complete graph is not just a special example. It's not just a particular example. It will actually be a very important graph, as we will see later on. Okay, so this theorems have to do essentially with the property of being prime and or a complete intersection. And then there's a second set of results more recently by Tolosa Villarreal dealing with two stronger properties. So this is the rational singularities or f-rational singularities in positive characteristics and unique factorization domain property. And again, there's a result of similar flavor. So there's another graph theoretic invariant. This is called KG. This is called the degeneracy number of a graph. But again, the combinatorial nature of this number is not really important for us. Just note that there is a way to produce an effective bound for each graph for when the LSS ring has a rational singularity. Actually, the theorem is about strongly f-regular, if I'm not mistaken. So something that implies f-rational and in characteristic 0 implies just rational singularities. And this is, again, in terms of this degeneracy number and the positive matching decomposition number that appeared earlier. And if you go one number higher, then you're guaranteed also to have the UFD condition. Once again, we can ask that maybe we want a uniform bound that works not only for, I mean, one sufficient condition that works for all graphs and vertices. So then this theorem of Tolosa-Villarreal produces the following corollary. Simply in terms of d and n, if d is at least 3n minus 4, we get a LSS ring that has a rational singularity. But for me, let me just write normal domain is the is a weaker condition, is the one that we will consider. And if we take d to be one higher, then we also get the factoriality of this ring. All right. So let me summarize what we just saw. Okay, so I'm going to write a theorem about this. So let me recap what we've seen. If we have a graph, a simple graph and then vertices, and you consider the LSS ring that defines the variety of orthogonal representations of G in K to the D, then we have some effective bounds for when this ring will become a reduced complete intersection, and then a domain, and then a normal domain, and then a UFD in terms of the data of D and N, in terms of the number of rows and number of columns in this matrix. Okay. So in our work with Laura, we improved these results. So our main theorem, or our first main theorem, is the following. And okay, so this is a very dense slide, so I'm gonna go very slow about it. But let me put it this way. So there is so we define three functions, okay, three numbers depending on n, three numerical functions that we call big D of complete intersection, big D of domain, and big D sub UFD. For the purpose of this talk, what these numbers exactly are is not really important. But something that is important is that these numbers are almost the same number. Almost always they are the same. They're literally the same number. And when they differ at most by 1. And roughly speaking, if we just want to get a quantitative idea of what number we're looking at, this is essentially 2n minus square root of 8n. Okay, and then these three, then these are our improved bounds for these properties. Okay, so we have one bound for granting the reduced complete intersection property. For domain and normal domain, these actually collapse into the same bound. So I'll just write directly normal domain if D is bigger than this function of n. And then same result with just a slightly bigger number sometimes for UFD. But these formulas are ugly and complicated, not because we like it this way, but because they are the correct bounds. So these are the best possible bounds that one can obtain in terms of D and N. Okay, so the bound for complete intersection. So the first one, this one is sharp for every n, in the sense that for every n, if I take D to be just one less than this integer, then there is an example that is not a complete intersection. And the same for domain. So if I, for every n, if I take D to be one less than this bound, then there is an example of a graph such that the ring is not even a domain, let alone a normal domain. So for 1 and 2, these are the correct bound in the sense that you cannot improve them in any case. For 3, not quite, but almost, in the sense that actually these two numbers are almost always the same integer. Okay, so and when I say almost always, I mean in a precise sense of measure theory. Okay, so this the set in which these two functions are different is a set of integers of density 0, and when they're not equal, they differ by 1. So for all those n, then this is sharp, so this is even sharper. I mean, it's just as sharp. There's just very few cases that are left in which there is maybe it might be possibly non-sharp by 1 integer. Okay, so actually I'm far from the 40-minute mark, but I think this is a good place for the break, because it's a natural point to split the talk in two. I will slightly change the notation in the second half. So yeah, maybe if there's
Okay.
questions or.
So I didn't see any question in the chat, but are there any question? Thank Alessio. Yes, David.
Hi.
I'm fascinated by this, actually, and interestingly, the rough bounds of that you presented first are very close to what would be true for just n equal to 2 in the case of a single quadric, right? And somehow that it seems to me also a very natural generalization of the theory of quadrics that you have. But you haven't shown us very much about the dependency on G yet, so I'm fascinated by that too.
Yeah, that's right. So you could worry about the dependence of G, and then you will get into the actual combinatorial part of this subject, where obviously changing the graph and changing the structure of the graph, the variety will be somehow affected by this. And this is the spirit of these two papers that have to that really. All of these are somehow some connectivity conditions, and also that's also the spirit of the original Lovász-Saks-Schrijver work and so on. Yeah, my point of view is to eliminate the combinatorics and just to drop all the dependency in the graph and work uniformly on D and N. This really is essentially the same as just working on the complete graph, where again you lose the combinatorics essentially.
Yeah. Right. Well, thank you.
Yeah.
I'll be back.
So are you going to tell us about the complete graph case also, or
Yeah,
is that still a conjecture?
The second part of the talk is all about the complete graph case.
Well, that's good. So I think we're gonna start. What time did we stop, Carl?
Maybe 2 minutes ago.
So I think we should start at 40. What do you think? So we are back. So Alessio, start back.
Okay. Yes. So
there is a comment from Jason.
yeah, I saw it. Yes. Yeah, I said something that is not quite correct about the non-effectiveness of Onion-Oxter's theorem, especially in the quadric case. There is an effective bound. Yeah, the general one again is not going to be the one we see in the special class of ideals. So thanks, Jason. Yeah, so as I anticipated, well, first of all, I'm going to explain the proof of this theorem, but really that really amounts to forgetting about G and we might as well focus on the complete graph to prove any of these theorems. Because of the following very simple observation. So if you have any graph on n vertices, so you could consider it as a subgraph of the complete graph on n vertices, assuming that the LSS ideal of the complete graph for KD is a complete intersection, and this is the weakest of all the assumptions we've seen, because, for instance, prime implies complete intersection, as we've seen. So in other words, assuming that all of the orthogonality relations for vectors in KD for our columns in the D by N generic matrix form a regular sequence, then the LSS ideal of a subgraph is just a subsequence of that regular sequence, right? So the entire set is a regular sequence. A graph will select some of them corresponding to the edges of the graph. That means that we can interpret the LSS ring as a deformation of the one for the complete graph, right? So specifically, we obtain the LSS ring of the complete graph from the one for some other graph by going modulo a regular sequence. And this behaves well with all of the conditions we've seen, especially being a regular sequence, obviously, but all the others are in some sense related to the singular locus, to the dimension of the singular locus. Okay, so long story short, the complete graph is the worst and therefore most interesting case to look at. So this is what I'll focus on for the remaining of the talk, and therefore I will simplify and change the notation a little bit. Right, so remember, we're looking at the space of D by N matrix, D by N matrices. So we have a generic D by N matrix X, H, J, and S is the polynomial ring of this affine space of matrices. So the ideal I'm interested in is what we've been calling the LSS ideal of the complete graph of its orthogonal representation in KD. And I'll simply denote it by EIDN. And this is the ideal where I take all of the orthogonality relations. Okay, so these are the relations when I get the dot product of the column I and column J in my generic matrix for all I and J different. And then the rest of the notation is essentially the same as before. So R will denote the coordinate ring. V is this affine variety of matrices, is the algebraic set that is cut out set theoretically by this ideal. So very concretely, it's parametrizing n tuples of vectors that are all pairwise orthogonal. So this we can call the variety of orthogonal frames as opposed to the variety of orthonormal frames. A frame is just an ordered set of vectors, so it's really a matrix. And this is extremely simple. This is just the set of all matrices that satisfy the following condition, that the A transpose times A is a diagonal matrix. So this looks very, very similar to what you would get if you replace orthogonal with orthonormal and therefore diagonal with identity. But this minor change makes all the difference in the world. So the resulting varieties are actually completely different. I mean, the orthonormal version is very well known. It's called the Stiefel manifold. When D is equal to N, it's just the orthogonal group. And in all cases, it is completely understood. But if we just relax the condition a little bit and just request that the vectors are only orthogonal, then the situation changes, as we will explain in a second. In any case, this is just the LSS ideal of the complete graph, together with its variety and ring. All right, so let's okay, the theorem that I had before the break now is essentially a consequence of the corresponding theorem for this ideal. Okay, and I've split it into the three different properties. So the first one will be about the complete intersection property, and for this ideal, three the conditions are usually different and increasingly strong, right? So equidimensional, complete intersection obviously implies equidimensional. Usually it's much stronger, but not in this case. And when it is a complete intersection, it will also automatically be radical. So all of these are completely characterized. We completely classify the pairs D and N when these conditions are satisfied. And again, the characterization is in terms of this numerical function that was more or less 2n minus root of 8n and has all these floor and ceiling functions and so on. And then we have the corresponding result for prime. So again, we see three conditions that are usually not equivalent at all that become equivalent for this ideal. So the weakest is the fact that the ideal defines, again, set theoretically, an irreducible variety. Two is that the ideal is prime, so that the coordinate ring is a domain, but then this will also give normality for free. And again, we characterize such pairs Dn for which these conditions hold in terms of this inequality that was seen earlier. So for complete intersection and for prime, we have a complete classification. For UFD, we don't. It's only at the moment a sufficient condition, but again, as I explained earlier, this number is almost always the same as this number, and therefore, whenever this happens, this is an if and an if. Okay, so these are our main theorems, and then the theorem about LSS ideal of arbitrary graphs is just a consequence of this, including the sharpness. The counterexample will always be the complete graph. So I will now start to talk about this, the proof of this theorem. So how do we get such classifications? And maybe it's a good time to do an example again, so to get concrete for a second. So I'm going to look at the case when D and N are equal to 6. This is an interesting first case for many interesting phenomena. But in any case, so these are square matrices even. And the variety V66 parametrizes all matrices where the columns are pairwise orthogonal with respect to this the dot product. Okay, so the most obvious example is the identity matrix, or you have literally orthogonal basis of K6. For instance, the standard basis. This is a point. This is a matrix in this variety. But you also have examples of a rather different nature. So here is an example where the vectors are all orthogonal to themselves, to each other, but also orthogonal to themselves. Okay, so So for instance, working in the complex numbers here, so this vector has norm equal to 0, right? It's orthogonal to itself. And and these three vectors are what we'll call isotropic. They're orthogonal to themselves, they're orthogonal to each other, and this means that also any linear combination of them will continue to be orthogonal to all of them. So here, the next three columns, I've just wrote down arbitrary linear combinations of the first three columns. And these are somewhat two extreme situations, and then of course you can have a mix of the two. So in the third example, I have three standard basis vector, and then an isotropic vector, and then two multiples of that last of the fourth column. Okay, so let's write down the terminology for these two different kinds of examples. So a vector that is orthogonal to itself is called isotropic. And so a vector's dot product with itself is 0. Norm, we could say it's 0, although there's not really a notion of norm. If it's not isotropic, or anisotropic maybe is a word. Okay, so so in this example, this was the example of the orthogonal basis, and they're all anisotropic. This is the opposite. All of them are isotropic, and we can also have a mix. 3 isotropic, 3 anisotropic. But this leads to a natural way to stratify this variety according to what could happen in terms of being isotropic or anisotropic, and what's the contribution of either type of vector. Okay, so I'll fix this notation. Let's introduce two new parameters, P and Q. So LPQ will denote the locus, the set of all matrices, where for simplicity, as in this example, the first vectors, the first few columns are anisotropic, and then the remaining columns are isotropic. If they're anisotropic and orthogonal, then they're automatically linearly independent, just like in regular linear algebra. But if they're isotropic, then that's not necessarily the case, as we've seen in this example, right? So we have 6 columns, but they only generate a subspace of dimension 3. So then we also keep track of this number, okay, of the dimension of the isotropic subspace they generate. And obviously they don't have to be ordered in this way. It could be that the anisotropic are last or they're mixed, but up to permutation. That's really the type of loci that we need to study. Okay, so then by our discussion, we have a stratification. So this is in fact a locally closed subset of this variety, and the variety is stratified by these loci. Okay, so all P and Q, if you really want to be precise, P plus Q is the rank, so it cannot be more than n, but in fact, there's a condition on how big an isotropic subspace can be, which tells you that P plus 2Q cannot be bigger than T. So up to rearranging the columns, which will just produce some different components maybe, these are the strata of which this matrix, this variety of matrices is made of. Okay, so so from this, so using this stratification, then I can discuss what are the main ingredients in the proofs of these theorems. So the first thing we do is a description of the strata. So this stratification is actually pretty nice. Each stratum in its own reduced structure is a smooth variety. It's irreducible. It's essentially irreducible. There's a few cases in which it's not, and then it has two identical connected components. But for our purposes, that's essentially the same as being irreducible. And we can determine the dimension of this completely. Okay, so this number will be a function of four variables: the d, the n, the p, and the q, and so it's a polynomial that depends on those four numbers. So that's the first main goal, to study each individual piece in this stratification. Then the next is to kind of understand how they're glued together. So in other words, to understand the generation problem of this stratification. Okay, so with a stratification, we can ask, when is one stratum in the closure of another? So if you want, this is a poset. So each the pairs P and Q defines a poset by this relation, and this is not a completely. This is a somewhat complicated problem. We don't really solve this problem completely, but we solve just as much as we need for the most interesting part of this problem. That is, where are the maximal elements in this poset? So where are the strata that are not in the closure or of anything else? So this is the same as finding all the irreducible components. So our main result in this direction is finding a complete description of all the irreducible components of this variety of orthogonal frames for all d and all n. And finally, for all, as we have seen, many of the conditions that we're interested in have to do somehow with the singularities or non-singularity of points and on the size of the singular locus. So then the last thing we need to do is to worry about the smoothness of the scheme this time. So here is when we actually need to distinguish what we've been calling the reduced algebraic variety defined by this ideal and the actual affine scheme defined by this ideal, by this ring. Okay, so let's denote it by x. X is the spectrum of the coordinate ring of the quotient by the ideal of the orthogonality relations. So the last main chunk of the work is to basically have a technique to construct many smooth points on some of these loci. There end up being smooth points on the scheme, and this is actually an interesting proof that has actually a translation into some condition about Hilbert function of certain general ideals. But yeah, I will not say any more than that. But once we have control over these three aspects, then we can prove all of the theorems. So for example, let's start with theorem 1, which was the one about complete intersection. Well, if we had the dimension of the variety, then and we had the number of generators of the ideals, it's just n choose 2. It's the number of pairs of columns. Then we can conclude. Then we can easily classify when this variety is a complete. This ideal is generated by a regular sequence. So this is already the step where we see those ugly numbers appearing, right? So this will be essentially some kind of optimization problem in terms of the polynomial that we get here for the dimension of these strata. So the solution of this optimization problem leads to the first of those ugly expressions with the floors and so on. But if we have complete intersection, then in particular we have comicoliness, we have Serre's property S2. So if we want to prove the ideal is radical by Serre's criterion, all we need is Serre's property are zero, so in other words, generically reduced. So, so here we will use ingredient 3, where we need to produce one smooth point for each irreducible component. And this can be done in all the cases where the ideal is a complete intersection. Okay, so that's the proof of theorem 1 about the complete intersection property. But then the rest is kind of similar. So if we want to prove prime, prime is reduced and irreducible. So irreducible is a statement about the irreducible components. So if that is from ingredient 2, where we understand all the reducible components, and then again, essentially by some kind of optimization problem, some numerical analysis, we can classify the cases where they're exactly one irreducible component. And reduced, we observed it earlier, it holds as soon as it is a complete intersection, so that's guaranteed. And then we get a classification for primeness. And again, just like in the previous theorem, for free, we go from domain to normal domain by, well, not exactly for free this time, okay? The idea, I mean, it's true all the times. That's what I wanted to say. The reason is the same. It's Serre's criterion, this time for normality. So, so then again, we are S2, which obviously is guaranteed by complete intersection, and then R1. Non-singular in codimension 1. So so at this point we'll have to be slightly more precise with the it's not just about exhibiting one smooth point in each irreducible component, but again it's something that we can do. We can control the size of the singular locus, so we get normality. And theorem 3 about UFD is again more of the same. This time the name is not Serre, it's Grothendieck, but there's a well-known theorem of Grothendieck that says that if you have a complete intersection and the singular locus is much smaller now, it has to be non-singular in codimension 3, then your domain is in fact a UFD. Okay, so I guess this is all I wanted to say in terms of our results. But there's a lot of interesting problems that remain open about this. They're really motivated by our study, and that's what I wanted to discuss next. If there are no questions. So, oh yes, no, actually no, there was one more result that I wanted to say. Yes, this was about this conjecture of Konka and Welker, right? That they conjectured that the LSS ideal of the complete graph is always radical, something that is not true for arbitrary graphs. And in our new notation, this is the same as saying that the affine scheme defined by taking all the orthogonality relations among the columns of the generic matrix is always reduced. Okay, so for every n and d, nothing to do with the previous complete intersection cases. So then again, this is something we can obtain not quite fully, but generically. So we can prove that this scheme is generically reduced, meaning there's a dense open subset where this is true. And so again, we're going to have to exhibit one smooth point for every irreducible component, and in general, there's going to be many, but this is something that can be done with our methods. Okay. So
question.
yeah,
This might be the right time for.
Mhm.
Of course, Cohen-Macaulay would get you from the theorem to the conjecture.
yes.
What do you know about XD and Cohen-Macaulay? I'm surprised you haven't told us about that.
No, I know, and the reason is that proving Cohen-Macaulayness can be hard, or estimating depth can be hard. So, for example, and this is one of the problems that I'm going to suggest, we don't really know anything about the free resolution of these ideals. There was this very recent paper by Gismundo, Wang, Weyman, and Schenk about the case D equals 2. And it's not Cohen-Macaulay in general, but again, Cohen-Macaulay is more than what we would need. Really, all we need is S2, and maybe this is expected, but it's really hard in some sense to estimate the depth. And the way we completely go around this problem by proving complete intersection, which is obviously very strong, but also something that you can prove easily by just dimension count. Yeah, so this is Cohen-Macaulayness is not something that holds in general, and maybe one could no, actually, Cohen-Macaulay here is equivalent to complete intersection, because complete intersection is equivalent to equidimensional, as I said. Yes. Yeah, so unfortunately, right. Yeah, so yeah, I will get to that. What I wanted to discuss in this final part of the talk is to just take a closer look at this irreducible components. I mean, at the some of the natural regions in this scheme, in this variety that is usually reducible as many components, but even the individual components are somewhat interesting. Okay, so, and I will just discuss two, which are essentially the two extreme cases, and then you can more or less get an idea that if you can control the extreme cases, then you can mix them and control the intermediate case. And when I say extreme and intermediate, it really means in terms of these numbers P and Q, that if you remember are essentially the ranks of the isotropic and the anisotropic parts of these matrices. Okay, so so one case is the following. So for simplicity, let me assume D is even. And then I want to look at the case when the P is equal to 0. So what that means, and also when Q is maximal given this, which means D half. And then I'm looking at the locus or the closure of this locus when P is 0 and Q is D half. So this is the variety of all the matrices. All the columns are isotropic. Okay, so they generate an isotropic subspace of the maximal possible dimension, which is D half. And okay, maybe the rank will drop in the closure, but then we drop this maximality condition. We're simply looking at the locus of matrices where all the columns are isotropic and also orthogonal to each other. Yeah, that's implicit in here. Right, so again, this is inside VDN. So okay, let's call this V iso for isotropic. Actually, this is a well-known variety. Maybe not so well-known, but it's a variety that has been essentially completely understood. And you could really think of it as an analog of the determinantal variety, where your group is no longer the general linear group, but it's the orthogonal group. This can be studied exactly as you do for the generic determinantal variety. So, so the most powerful technique for proving things would be applying Weymann's geometric technique for calculating syzygies. And if you do that, you basically get everything. I mean, a corresponding result for this variety, as in all the other results that you know about determinantal varieties. So first of all, you find the generators of the prime ideal, and these are the obvious ones. These are the orthogonality relations plus the minors of size, I guess, d half plus 1. In any case, whatever comes out of the fact that an isotropic subspace cannot be too big. So this includes a rank condition on these matrices. So there are no surprises in some sense on the generators of the prime ideal. And the nice fact is that that ideal is prime. You can also determine its free resolution, its equivariant free resolution. And you can prove the strongest of all the properties we've seen, I guess, except for UFD, that is this variety has rational singularities. So it is normal Quemicoli. It's not literally a complete intersection, but it is a complete intersection inside a determinantal variety. And I don't know who to attribute all these results to, but because this appears in Weymann's book as an exercise, but I'm guessing that he actually was the first to prove all these theorems. And there's no reference, so maybe it was just being modest and it just presented it as an exercise. But I don't know. Anyway, this variety, the one where everything is isotropic, is actually well understood, completely understood, I would say. At the other extreme, we have, so we'll now switch the tool roles of P and Q. So at the other extreme, we get the one when Q is 0 and P is as big as possible. So again, for simplicity, let's assume that N is at most D, so which means our matrices have at most as many columns as rows. But then this locus is even more natural than the one we were considering earlier. So this is so ln0 is really the variety of orthogonal bases, not just orthogonal frames, but vectors that are orthogonal to each other, but also linearly independent. And then we take the closure of this locus. And now, so this is what we would call the main component of the variety of orthogonal frames. Also because this is always a component. The previous one, this one is not always a component. If depending on the relations between D and N, sometimes this is a component, sometimes this is a very small locus and it's not a component in our variety. It's just a locus of positive codimension. But if we go in the other extreme where we request that our vectors generically are linearly independent, then this is a full irreducible component just by semi-continuity of rank. And it's the most natural part of our variety, right? So for instance, if n is equal to d, then this is the variety of orthogonal bases. This is not so well understood. So all the things that I showed in the previous slide here are open problems. So we don't understand the generators of the prime ideal. Okay, so except in the obvious case when there's no other components. So I said that this is the main component. So whenever the variety VDN is irreducible, which is what we characterized here, then these two are the same, and then we understand it's the ideal. But other than that, we don't understand the ideal of the variety of orthogonal bases. Even in this example, so I wanted to include this particular example because everybody that I talk to doesn't believe me that we do not know the answer to this question. Okay, so C6 or even R6, we can even take a non-algebraically closed field for this example. You take the variety of all orthogonal bases. This form an irreducible variety in the space of 6 by 6 matrices. What are the equations of these varieties? That's unknown. But again, maybe it's not so surprising that the answer is unknown, because the answer somehow has to factor this bound inside the answer, because this ideal will be the LSS ideal if and only if this inequality is satisfied. So whenever this ugly inequality is not satisfied, we absolutely need some new equations in this prime ideal. And obviously, it would be nice to ask for its free resolutions, but if we don't even know the generators of the ideal, this seems unlikely at the moment. And then all of the singularities that we have investigated, whether it's normal, Coimé-Colli, rational singularities, or even UFD, these are natural questions. Again, this variety will coincide with the variety VDN, and therefore with the variety of the LSS ideal when this is sufficiently large. So all of these will hold for d sufficiently large, specifically the bounds that I've been discussing this entire talk. But it is very natural to believe that maybe the first three will hold for every d and n. I don't know. But these are definitely some extremely interesting problems, especially if we think about the parallel with the theory of determinantal varieties that is well understood for decades now. Maybe let me just say, what is the difficulty in this problem? The difficulty is that unlike the case of determinantal varieties, when we close this locus, we don't just introduce the similar matrices of lower rank, but we'll also introduce the generations to isotropic subspaces. So the problem is that the bilinear form, when you restrict it to those subspaces, the rank of the bilinear form drops as well. So resolution of singularities will have to account for this, not just for the rank drop in the matrices, but also for the rank drop in the restriction of the dot product to all of these subspaces. And then there's two more open problems that I wanted to mention. One is in principle simpler than what I just discussed. So not just the free resolution of the main component, but the free resolution of the entire scheme. So then remember, this is just the ideal of orthogonality relations. You take all of n choose 2 orthogonality relations of your d by n generic matrix, you get an ideal generated by quadrics. Can we compute its free resolution? And again, this is maybe more doable, but still quite challenging. So the case when d is equal to 2 was just completed in this work. But this was thinking about this ideal as an ideal of permanence. And when these two permanental edge ideals, analysis ideal, the ideal of permanence of a generic matrix and the ideal of orthogonality conditions of a generic matrix are the same. But then when d increases, these are two different generalizations, right? So So this is somewhat analogous to the Pfaffians and the ideal of the Grossmanians. When you have a matrix with two rows, these are the same, but then you have different generalization. Anyway, that's an interesting open problem. And then the last open problem is a natural problem about the primary decompositions of LSS ideals. We know these can be non-radical in general. We don't know if that can happen for complete graphs. Maybe it can, maybe it cannot. We don't know. But an ideal can be non-radical for two reasons, either because a minimal component is not prime, or because there's an embedded prime. And we don't know any examples where there is an embedded prime. So that would be a way to complete the proof of Conca and Belker's conjecture. Okay, so I finished. I'm going to stop here.
Thank you, Alessio. Are there any questions?
What sort of ideal theoretic properties did the combinatorialists look at? Presumably not these.
Right. So one interesting outcome I can say for the combinatorics was this introduction. So this theory of LSS ideals and the search for effective bounds for instance, the prime property led to this definition of positive by Conca and Belker of positive matching decomposition number, which is a completely combinatorial concept that I haven't discussed, but then this was taken up by at least some combinatorial people, and there's a few conjectures purely in combinatorial terms related to this. But as far as I know, the ideals themselves have mostly been studied from commutative algebra people, especially if you take D higher than 2, right? So the edge ideals are their own story. The permanental edge ideals maybe are somewhat in between. But then if D is higher, then as we've seen, this is maybe more closely related to the theory of determinantal varieties than to the to graph theory. Or yeah, that's not really an answer to your question, but yes, not that I can think of.
And if there are no more questions, I would like to thank Alessio again. So
Thank you all for coming.
Alessio, thank you for the very, very nice talk.
Thank you, Alessio. Great talk. Thank you.
Thank you. Thanks.
Yeah.
Okay.